I'm back. I've had a few emails come in, I don't know how, but they did, and from students asking, wanting some clarification on questions about figuring out unknown structures from the NMR spectra. Now, if this was the face-to-face version of the class, I would probably have used, every professor's secret weapon, read the book, and gone on and counting on the fact that it would probably take the students a good week or two to realize there wasn't a book in the class, and kind of chuckling on my way and get on with it. But we don't have that option here. I could still say read the book, but again, we don't have one. And being a summer class, I certainly have plenty of other important things to be doing right now. But I decided to go ahead and, in a class where the students have to watch some of my crappy videos, that the answer to the problem was to make another crappy video. So here I am. What I'm going to do is go through a couple of the unknowns on the Friday assignment for the chemical shift module, the one we're in right now. And what I wanted to do is go through the spectra and try to demonstrate for the group how I look at a set of spectra and try to determine the puzzle pieces, the pieces that I have to think about when I'm trying to put together a structure. I'm not going to solve the structure completely because, let's face it, what would be the sport in that? But I do want to kind of essentially come up with an inventory of pieces and clue you in onto the things that I look for. Now, some of you are pretty good at this already, and that's great. Some of you have had decent enough experience with it. Others may not have seen much of this at all. So, this is for everybody in the class, but certainly for folks who might, be struggling with, how do I begin actually determining these chemical structures. So, looking at the set of spectra for the Friday assignment in the chemical shift module, and they're on the course website right now, a collection of PowerPoint files. There is a collection of spectra for what I call basic alcohols, and we're going to leave those. I'll leave those for you guys to work on. But I do want you to look at the set of spectra labeled the basic unknown. And you have no other information about this thing other than it's an unknown molecule, no formula or any other thing like that. We get into a later module in how we use formulas and sample histories to help us with our structure determinations. But for right now, this is all we have are these pieces. So what I usually do when I'm confronted with an unknown like that is I start doing what we've been doing in class so far. Start taking an inventory of the pieces. And so looking at this one for a moment, I am going to take a look at the number of hydrogen groups. Okay, number of hydrogen groups in this thing. And looking at it here, there seems to be 5 groups. And they are in a 2 to 1 to 2 to 2 to 3 ratio. Seems to be a total of 10 hydrogens in this molecule. And remember, that could imply 10 hydrogens, or it could imply a greater number if the molecule has a significant amount of symmetry. But we're looking for certainly at least 10 hydrogens in this thing, because these are all the smallest whole number ratios possible. Then the number of carbons, okay, and the number of distinct carbons, okay, carbon 13's in here. We seem to have, yep, there it is, 7 carbons, 7 distinct carbons. Now there could be more, of course, than 7 carbons. There's at least 7. There could be more if the molecule has any symmetry. So just looking at the number of peaks and their integrations for the proton spectra, this is what we have. Our new tool in the toolbox is the chemical shifts, and it's a very powerful one. And so now I start looking at the chemical shifts. Of course, remember, we're trying to learn how to drink from the fire hose of information. We take this very piecemeal, one bit or set of information at a time, and then start putting things together. And the chemical shifts for this thing are very useful. Notice that these 3 protons in the molecule are at chemical shift range. We have 5 hydrogens at 7 to 8 ppm. Okay, 5 hydrogens, 7 to 8 ppm. Oh my goodness! I mean, there's just no way that these spectra could scream any more loudly than to say we have an aromatic ring with one substituent on it. Okay, so remember, there's something here at that position. It's not a methyl group necessarily, but there are the 5 carbons, or there are the 5, excuse me, hydrogens, the ortho and meta positions integrating to 2, the para position integrating to 1, 5 total. And to confirm that, you can now switch over to the carbon spectra, and sure enough, you see 4 carbons at 120 to 140 ppm, which is exactly what we would expect to see from an aromatic ring like this. 1, 2, 3, 4. Okay, the aromatic ring has its symmetry. So the ortho and the meta positions are, 2 different carbons, but 1 group each. And so that, we have beautiful evidence, irrefutable evidence that we have this aromatic ring in the molecule. So this, and I'm going to go ahead and reproduce it over here, is one of my puzzle pieces. And I know this absolutely. Okay, there's no question about this one. Okay? All right, looking at some of the other things here, I see 2 hydrogens at, and let's see, the exact value that I got looking at the spectra was 4.3 ppm. Okay, 2 hydrogens at 4.3 ppm. Almost certainly then, this is the distinctive chemical shift range of protons. Did I write a 3? That was stupid. CH2 group near an oxygen. Okay, I mean that range around 4 plus or minus about a half ppm either way is very distinctive for oxygens and ethers and esters and alcohols, those types of functional groups. So we certainly have a CH2 group, extremely likely have a CH2 group next to an oxygen. Again, combining this information with the carbon spectra, I do see a carbon at, and this is about 60 ppm, yeah, about 60 ppm, which could well be that, CH2 group. Okay? So I'm going to add to my collection of puzzle pieces that fragment here. And then I see 3 hydrogens at 1.3 ppm. Okay? Now, 3 hydrogens at 1.3. Again, it can't scream much louder that has got to be a methyl group. Okay?